To the RoboCup Symposium. For me, this is the most important day of RoboCup. I always tell my students that this is the day we can't miss of the symposium, of the RoboCup. I have two announcements. One is that there is open Wi-Fi here. It's called Symposium. It's without passwords, so you can use during the symposium. And also that the symposium proceedings are on the website. You can have the QR code or the URL in the booklet, so you can see the papers. And without further delay, I'm inviting Manuela Veloso to introduce our first speaker.
Okay, thank you, Reynaldo. Welcome all again. So it's my great pleasure to introduce our first invited speaker, who I don't think needs an introduction, but I'll try. Just two words. So Rod Brooks is a professor currently running a company, Rethink Robotics. He was a professor at MIT for many years. As you all know, he started robotics very early on and introduced the subsumption architecture, which we all know about. And he then started a company, the iRobot company. And currently, like I said, has this manipulator Baxter, Rethink Robotics, and Rod will tell us about it. So I've been a fan for many years and a good friend too. So Rod, let's welcome Rodney Brooks.
Welcome everyone. Thanks for coming. Thanks for getting up this morning after the banquet.
Okay. Oh, talk quietly. Hello, everybody. So, when the slides come up, there's lots of people walking. What I thought I would do today is two things. First, that's it. It's good. First, I'm going to talk about what I think the challenges for
Robotics.
The first challenge.
Okay.
Hello?
Okay. So, I'm a little confused here, but we'll get there. So, here's the question. We all came here, we all build robots. Why do we do what we do? Why do we all build robots? What's the motivation that we have? And it may be different for different people, but I think there's a bunch of motivations for working with robots. One is it's fun. Some people just want to have fun. For some, it helps us understand what it means to be intelligent. It helps us understand us. For others, it helps us with other parts of science, so we use robots to study other parts of science. And for some of us, it's leading to better lives for people, improving the lives of everyone. So I want to talk about some examples of that. First, it's fun. In the United States, we have the first robot league, the first robot competitions, where hundreds of thousands of students, build robots, largely motivated by fun, but then out of that comes education for high school students. So it's a great program. Another thing people do is to build robots to understand intelligence, to understand us. And actually, this has been going on for a long time. I don't know whether people have heard of Gray Walter. He built robots He built robots back in 1949 and 1950. And these are the first mobile robots with intelligence that I could find. He was actually someone who studied the human brain, but he built these simple robots in order to build models of a simple brain. Now this is 1950, so in 1950 there wasn't, easy technology around. His robots had two motors. They had two vacuum tubes and some relays, so nothing like a processor, and just very few sensors, single bump sensor, a light sensor, etc. And with this is the circuit. There are these are vacuum tubes, light bulbs with shields in them, two vacuum tubes, very simple circuit, but he got lots and lots of behaviors out of these because these devices are non-linear as the voltage changes. And I'm not sure many people have seen this, but this, I'm going to show you now, is the very first robot video ever. It's from the BBC in the early 50s. But it's got a lot of characteristics of all the robot videos everyone builds today. So here we go. Is the sound on? Sound for that? No. No sound, huh? Maybe. No, no sound.
Dr. Gray Walter, a neurologist, who makes robots as a hobby. They are small and he doesn't dress them up to look like men. He calls them tortoises. And so cunningly have their insides been designed that they respond to the stimuli of light and touch in a completely lifelike manner. And she sees out of a photoelectric cell which rotates above her body. When light strikes the cell, driving and steering mechanism sends her hurrying towards it. But if she brushes against any object in her path, contacts are operated that turn the steering away. And so, automatically, she takes avoiding action.
This is my favorite shot, the admiring look of the scientist at the robot. Anyway, it goes on, it shows how the robots, when they run out of battery, they go into the hutch, attracted by light, and recharge themselves, etc. And that's what inspired me. This is my very first robot. Unfortunately, this is after it had been in my mother's garden shed for 30 years, but this I built when I was a teenager, and tried to build a transistorized version of Gray Walter's robots. Another thing that robots are used for science, for other fields. And in particular, I was inspired, the reason we started the company iRobot was a space exploration company. We wanted to send robots to other planets. That was our original goal. We worked hard on building small robots that might go to other planets. And we worked with various organizations. This is actually a test launch we did in 1993. We have a 6-legged robot sitting here inside a 23-kilogram brilliant pebble, which had enough delta V to get from the lunar orbit to the surface of the moon. And this was a test of deploying our robot, and it was going to land next to the Apollo 15 lander and do some metallurgy on that. So
10 feet away, 14, 13,
this
12,
is Air Force
11,
Base. Just a test. We hadn't flown the robot for 4 days. It had been hibernating as it was getting up to the moon.
receive 3, 2, 1, 0.
Well, this is doing a soft landing, which we were going to do on the moon.
Plus 6, plus 7, plus 8,
After it lands,
plus 10, 11.
kicks out a pod here. Well, kicks out a pod, and the robot is in there. The robot now wakes up, realizes it's on the moon. You'll see its rear leg here where it undoes this pod and gets itself out.
25.
Now it stands up, and off it goes to do its metallurgy. This was a great success. the government agency, which was not NASA, which had this, said they were going to send it to the moon, and then NASA got really upset by that and said, but wait, we have a mission to Mars coming up, and we have this little robot program at JPL, which Colin Angle and I had also started. They said, we're going to spend $25 million extra and send a robot to Mars. And that's how Sojourner got to Mars. So Sojourner landed on July 4th, 1997. It wasn't originally planned to go on the mission. And for the first 28 days, they used conventional control. And on day 29, when the secondary mission was even over, then they turned on the behavior-based control, and it ran until day 84, exploring Mars. And then the lander failed. So this is a picture from the lander, and there you see a picture of the robot off in the distance. So we did get to explore Mars, but in a slightly different way than we thought. And at iRobot, we realized that that was not a way to make money trying to do science. So we better try and make people's lives better. And I want to give you two stories. I'm a little out of sync here. I want to tell you a couple of stories about getting robots to do real things in the world. We all know that software is really important for robots, and a lot of what happens in robot software is better software, better software, better software. But we also need better hardware, and hardware is important. Hardware enables the software, so we can't ignore the hardware. So, two stories. First one, this is the very first robot vacuum cleaner that I built in 1992. It was built in my lab at MIT. The control boards here were built by iRobot, but this was built by my students. We weren't very good at designing things. It sucked all the dirty air through the computer boards, which was a design flaw. But it had beacons and it could detect people. But it was from then, 1992, it's 10 years of developing hardware before we got to a commercial product that we could first sell, the Roomba. And the Roomba came out, and lots of people bought it. There have been, I think, 12 million of them sold by now. But it wasn't perfect by a long shot. It had many, many problems. One of the problems was that it would eat cords in people's floor and get caught up and tangled up. So after about 5 years, we developed a way to detect that and unroll it from the brushes. And so after 5 years, the Roomba didn't have trouble with cords and tassels. But the brushes under the robot got tangled up with hair and dirt. And if you read the instructions that came with the robot, it said, clean the brushes every month. No one ever cleaned the brushes. It's dirty, it's disgusting. And it wasn't for 11 years until iRobot came up with a solution, which was largely a mechanical solution to that problem. Because there just wasn't a way to do the sensing and the computation and what to do about it. So the lesson from that is we couldn't find a way to sense the world enough to know about hairs and know what to do with it. We had to have a mechanical solution. Because, you know, we like to think of the world state, but sometimes we just can't know the world state. We have to live without that. So we have to come up with other ways of doing things. Does anyone know what this is? Sorry? Mercedes? Any other guesses what it is? Sorry? Yeah, robot, what was that? That's the name of the car? No. Oh, okay. Maybe. But this is what I say this is. I say, oops. Oh, pressed too fast. I say it's an elder care robot. Because it is a Mercedes, it is the S-Class Mercedes, and has lots and lots and lots of automatic driving features and safety features. So what does that mean? That means as I get older, I can drive a car like that and be safer than I would if I was driving a simpler car. Now, you might say, oh, well, Mercedes are expensive, you know, only the rich people will be able to have Mercedes. But they said that about Mercedes when they first came out with automatic braking system, with ABB, sorry. anti-lock braking systems. When they first came out, they were only in Mercedes. Now they've moved it all the way down to Kias in every car. Wherever if you buy a car in a place which has winter ice, every single car now has anti-lock brakes. So the technology in these cars, these self-driving technologies, start in the high-end cars and trickle down to the low-end cars. So it's something which will enable people to drive more safely longer. That's why I call it an elder care robot. But it is a robot. Cars have become robots. Oops. Slow. When I came to the United States from Australia in 1977, there were only 3 mobile robots in the world that I could find. Now, we've seen, I don't know, how many mobile robots were here this week? 5,000? 500 at least. They're everywhere. But in 1977, there were only 3. There was one in Toulouse, one in Pasadena, which was really teleop controlled, and one in Stanford. And the 2 on the outside were autonomous robots. But it was really, really early days. And people started thinking about how to build maps as these robots moved around. Both the group in France and people at Stanford were trying to build maps as the robot moved around. But there were lots of technical challenges to it. This is the first mobile robot I built at MIT in 1984. And in 1985, both myself and Chatila and Lamont were writing papers about how to build maps, and we came up with loop closing, which is a core of SLAM these days. But we had terrible statistical models. The next year, Cheeseman came up with better statistical models, and by about 1991, quite a few years later, John Leonard and Hugh Durant-White formalized simultaneous localization and mapping, but still, the algorithms were really rather poor. But what happened, and this is a critical thing, around that time, low-cost platforms started to come. Sorry? Oh, I changed. Thank you. You're in charge. Low-cost platforms started to come. So at the time that, in 1985, when Raja Chatila and Lamond and I published papers about loop closing, there were maybe 10, 15 people working on robot mapmaking. But by the late 80s and into the 90s, it turned into hundreds of people and then thousands of people. And with the formalization of SLAM, then people started to make progress. And it was because there was lots and lots of people having lots of ideas, testing ideas, comparing ideas. But it wouldn't have happened if we didn't have low-cost platforms that lots and lots of people can use. And that's why robot soccer works so well, because the cost of a platform, suppose every robot soccer robot cost $1 million. How many teams would we have from around the world? Not many. It's because the cost is low. It lets lots of people work on things. And when lots of people work on things, then the great progress happens. It doesn't happen by one person working and thinking great thoughts. Unless you're Einstein or Newton, and there's not many Einsteins and Newtons. So we have to have, where there's technology and engineering, we need lots and lots of people working on the same sets of problems. And that's what's happened in the Robot Soccer League. Lots and lots of people. And the problems have changed over time, but it's so many people working on it. So it's those low-cost platforms. And then people use these to build maps. And out of that came the technology for that elder care robot. The SLAM technology led to various competitions, cars, self-driving. Google car showed what could be done, and that goes into the mainstream. It takes, 25, 30 years to get there from the start to the finish, but that's the path we see. Few people think about some ideas, then low-cost hardware, so lots and lots of people can work on the ideas, and then it changes the world. So how do we need the world changed now? Where are robots important if we're going to make people, if we're going to make people's lives better? Well, I think the biggest thing that's going to drive robots is this. It's the changing demographic in much of the world. This is the percentage of adults who are working age. And it's gone down slightly over the last 40 years, but it's about to change radically. In China, in the US, in Europe, the percentage of adults who are not retired is going to drop dramatically. And so there's going to be less people in working age to provide services for those elderly people. And we see some implications of this. Right here, we see those tall buildings full of apartments where people from Europe are coming here to Brazil to retire because they can get better services here in Brazil by moving than they can in Europe, where there's not enough working age people to provide services. So I think this is really going to drive needing robotics to help people as they get elderly and to replace the workforce. In China, China has been the place where we've had low-cost labor for the last 30 years. In China, the absolute number of 19-year-olds is going to drop by 30% over the next 10 years. The 19-year-olds are the ones who go into the factories. So labor problems are going to become incredible in China for the factories, let alone for elder care. So, like the Mercedes is an elder care robot, it lets people have dignity, have control of their lives longer. There's going to be a real pull for robots to help people as they get older, and so that, Manuela, you're a long way from being older, but in another 50 years, even you will start to get older, and you'll need some help. But me, it's really happening soon. So, how are we going to have robots to help us maintain our dignity, maintain control of our lives, and live longer in our native ways? And I think there are three great challenges for robotics about this. In the old days, we used to talk about the 3 Ds of robotics: dirty, dangerous, and dull. I'm going to talk about the 3 M's of robotics: mobility, manipulation, and messiness. These, I think, are 3 challenges for robots. And what I want to talk about now is the availability of low-cost hardware to help solve these 3 problems and whether it's around. Let's talk about mobility. If we're going to have robots help the elderly, the robots have to be in their houses. They have to get around the house. With the Roomba, it can get around on a single floor, and we made it so it doesn't fall downstairs, but it can't go up and downstairs. But if you look at people's houses, even a simple house on the side of the street will often have a step up into the house. So if the robot is going to help the person, an elderly person, get their groceries into the house, say, it's got to deal with steps. So you see steps going into houses, and then inside houses, you see lots of staircases. And if you hire an architect, the staircases get much more elaborate and difficult. In our robotics research, RAM, can any of your robots deal with these staircases yet? Not yet. Yes, that's the point. So, do we have hardware which is going to let researchers deal with mobility of houses? And what we have, well, at iRobot, we have the PackBot, which can certainly go up and down stairs, but it's meant for war zones and nuclear power plants that have failed. You don't want one of these in your house. It's going to mess up your stairs. The Japanese robots, well, how many of them are there? There's not that many of them. Maybe 50, maybe 100, I don't know. And they're not that good at stairs. The Atlas, 10 or 12 of them in the world, and you definitely don't want one of these in your house. So I'm afraid in mobility, walking robots, things that can go up and down stairs, we don't have much. Now we have, here in this audience, lots of people building legged robots, programming legged robots. Unfortunately, soccer is flat, so you're not worrying about these challenges. But I think this is a real challenge, but there's no hardware that's massively available for people to work on. I know, Ram, you've been struggling to buy some robots. It's tricky right now. So mobility, I think, is wide open for low-cost hardware, and then I think there are enough people interested in mobility that things will start to happen. and a lot of them will have come from robot soccer. Second thing, manipulation. These things we have on the end of our arms are amazing, totally amazing devices. Da Vinci knew how amazing those devices were. He was fascinated by them. But we don't have dexterous robots. One of the famous recent success stories is the Kiva system for packing, where the brilliance was to partition the problem into two parts. Something that a robot could do easily, which is move in a straight line. And so the shelves are brought to a picking station, and at the picking station, a person with their dexterous hands picks the things out of the shelves. So the person no longer has to run from shelf to shelf. The person just stands there, the shelves come to them and they pick. But no one has got a robot which can do that picking, of reaching into a bin, picking an arbitrary object out of it. So, what's the likelihood of progress on manipulation? And, again, soccer is not really about using your hands, so it's not a challenge in soccer. Well, people have built complex hands, but you have to put them on an arm. Arms are dangerous. So, with the Baxter robot, notice it has no hands here. One of the main reasons that we made it available as a research robot was hoping that people would then start to use it as a platform to try out different hands on, because at least the arms would be safe and it was easy to use and low cost. But I think there's a bunch of challenges on building better hands and better manipulation. The challenge is you can't just do one thing at once. You have to make progress on the mechanisms, on the sensors, on the materials, and the algorithms. And if you're also worrying about arms, that's too much to worry about. In fact, anyone who can do two of these at the same time is got to be very smart. But I think, just pushing on one of them, you get held up by the others. All four are important. Materials are very important because we use the softness and the different material properties of our skin as part of the grasping. It's very important. The sensors that you have are very important. The mechanisms are very important. And only when you've got them do you start to figure out what the right algorithms are. Until you have all those pieces. So there's a lot of chicken and egg problems here. How do you move them? So I think this is a real challenge. But at least now we've got safe arms that we can put the hands on the end of. The third one, messiness, is a bit better story. Oops. I stole this from someone's paper about robotics in the kitchen. This was their model of a kitchen. And then I stole this from Aaron Edsinger's PhD thesis. This is his kitchen. You notice the difference? So if you're doing your research here, it's not going to work there. So the good news on the messiness problem is video games. There's just been a whole lot of low-cost 3D sensors around. And this is really changing, I think, the research in this area. Because getting 3D data used to be hard, now it's easy. And so of the three challenges, this I think is the one where things are moving fastest because so many people can have high quality, low cost 3D data now. So that's a success, that's great. In terms of the robot, and here's a request for you, in terms of Baxter as a robot for manipulation, we're now distributing them around the world, Shanghai, Tokyo, but notice there's no South American distributors here. If anyone has a South American distributor to recommend, please come to me, because we'd like to make them available in this region of the world too. We've started to go rest. But now I want to change gears. They're the challenges, and now I just want to show you what we're doing with Baxter as an application robot in manufacturing. So this is the robot. We do sell it as a research robot, but that's not its primary role. Its primary role is for manufacturing, and we sell much more of them into manufacturing. And I want to show you some of the things that we're doing. Our way of thinking about these robots is that they should be robots and people working together. So here you see two Baxters and a woman working with them. Here you see a person and a robot This person is putting things in blister packs. It rotates through a heat treating machine here, comes out here, and unpacks them and puts them on a conveyor belt. But it's robots working side by side with people, and that you don't program the robots. You show them the task. There is no programming in these robots in factories. Not a single line of code. There is no code representation. So here's a couple of robots working in this is a factory that makes very low-cost plastic furniture kits, and the woman is doing some inspection and feeding parts, and then the robots are with custom-made grippers, 3D printed fingers there, and plumbing supplies to make a suction gripper there, picking up the parts and putting together kits of plastic parts. So a simple task, but in close proximity. And we're using a whole bunch of capabilities to make this easy to get the robot to do tasks. Again, no programming here. The robot just knows how to do this, so you show it stuff. So let me show you the series elastic actuators, which are in the robot. There you see a representation of the force that each joint is feeling. Notice that this joint is load-bearing, so that there's a lot amount of force. This joint is not load-bearing, so there's low force. But as the person moves the arm around, we sense each force, put those through a Jacobian, and out of that you get 3-dimensional or 6-dimensional force vectors, so you can sense when there's a disturbance. So whenever the robot arm is moving, it has a forward model of what forces to expect, and if it feels a different force, then it knows there's a collision. It can back off in just a few milliseconds. And so these robot arms are very safe to interact with. And I'm not sure whether this is a good idea, but all the engineers at my company know that on any day, I may just come up to a robot and put my head in the way. You know, if they don't like me, but they do tend to try to keep the robots safe. So once you have force measurement, you can use robots in a different way than traditional industrial robots operate. Traditional industrial robots use accurate position control. Instead, we use our robots to place and align by force. This is a sheet metal being put into a fixture and slide until force. This is actually a model of what a real customer is doing in their factory, where this is a press brake, where someone puts a sheet metal in, lines it, presses a pedal, and it bends the metal. Almost none of our customers will let us film inside their factories. In this case, because the factory is so hot and horrible, they don't want it seen. But this is exactly the same task, where we slide till we feel the force and align to the fixture. And again, no programming for this, just showing the robot what. Next thing is place with contact detection. Here we're putting again from a customer, we're putting a circuit board to 200 micron resolution in a fixture for some other machine to operate on it, but it's sliding until it feels force. The old Lozano, Perez, Mason, and Taylor idea here. And there, a person put their hand, it felt the force, it let go. So it's feeling the forces. Next, is placed with force sensing and compliance. So now we couple a couple of things here. It's using vision to pick this up, and then it's going over and doing peg in the hole with force. He's going to pick that up, he's going to put it in a different position, about a centimeter back from where it was. The robot finds it with vision, and then detects the force at fairly high speed and does the insertion. If a person is working on assembling things, they don't do it by position control, they do it by feeling forces and a sense of touch. So this robot now has a sense of touch. Let me run that one again. You'll see the part is forward next to the line. Is this running? Oh, I may have stopped it. Back. Now, That's right. I think it's right. Are you touching it? No, one. No. I think. Yeah, okay. Okay. And then you'll see it pick up from a different location and do it again. I'll try this for the next one. Now I'm going to show you, so this is all in the current software that was released this week. Now I'm going to show you something that's not in the current software, will be in the next version. We're putting these robots into small factories. In small factories, they're not very well controlled environments. Things move around, short runs. It's not bolted down, it's not hardwired. So this lets us do work in factories where things move around a lot by having fiducials. So we have a couple of fiducials here that are visible. We have fiducials on the conveyor belt. And when the robot was trained, it was told to register its actions relative to those fiducials. And this camera up here in the head is watching the fiducials and seeing if they move. And if they move, it says, uh-oh, things have changed. So he moves them. And now the robot says, look, these two fiducials have moved. I better find out where they are. It uses its hand camera, and he tells it to use the hand camera. This may become automatic in the real software. Uses the hand camera to find the fiducial, says, yeah, I got it, green, I see it, I see it, I see it, I see it. Calibrating, oh, I can't reach that location. It's too far away. So it asks the person to put things back to a closer position. So he does that. Now it registers, calibrates again, everything's green. It says good. Now he tells the other arm to go and register the other, the fiducial that it knows about. It goes and does that. But everything is in a different location than it was originally. The robot has adapted to where things are, and now can do things fast again without having to use vision on every cycle. Because if you use vision on every cycle, it slows things down. This is the task map on the face of the robot. So now it's able to go pick those things up in a different location and precisely align them. Again, on the conveyor. Conveyor's not running here. Let me show you another thing, those 3D sensors I talked about. And here's one of the great powers of ROS, which we use in the robot. We can just send ROS messages to the robot from an external device without having to integrate it. So here we have a 3D sensor, which is detecting parts presence or absence. And this is not such a great demo for a lab, but remember, this has to work in a factory. Factory workers who know nothing about robots, and they have to be able to use it. So here, it's waiting till a part is present, using a 3D sensor to tell when it's present. There are no parts on the right, so this arm is just waiting there, and then it's putting them on the conveyor. And you see here where the color changes when a part is there or not. The conveyor, it's waiting for the room on the conveyor, and we're just sending ROS messages to the robot to tell it that, but we're also detecting these fiducials again from the 3D sensor. And so, in a second, someone's going to come and bump the table again, and the 3D sensor is going to automatically re-register to the table. Again, as a lab demo, not so impressive, but something that just works every day in the factory where there's no one with a PhD there. And there you see the sensitive regions moved with the table. So that's the sort of thing that we're putting into our robot to make it easy to use in factories. Things that we haven't had in factories before. Things that are coordinate system independent, etc. But one of the really important things is, and I think you all know this, especially people working in the standard leads, that you can have the same hardware with better and better algorithms and better performance. So that has not been the case in industrial robots before, but we're bringing that idea to industrial robots. This is, can we switch the sound off? Yeah. So this is Baxter, the same robot. This is doing a customer task. The customer that does this has put millions and millions of these in boxes now. But this is the software over there on the left from a year ago. This is today's software. And you'll see that today's software is so much faster. Why is it faster? Well, there are all sorts of reasons. One, this spring here, which is gravity compensating, it's a spring that's got a little pinion that goes around. There's stiction there, so there's hysteresis in that. And if we don't model the hysteresis, we get inaccuracy when we move. By modeling the hysteresis, we get better. So here, the part count is 15 compared to 3. It's going to sort of catch up. But the robot is much faster, much more precise the way it moves. So over a year, the robot has got almost 3 times as fast and twice as precise, just from software. And I think, you know, I saw, you know, how well some robots walked, how they were faster than other people. So, you know, everyone here is aware of that idea of improving things through software. So here it's just finishing, puts the separator in, and part count of 30 versus now 12. And so in the today's software, it took 1 minute and 12 seconds. A year ago, exactly the same hardware, took 3 minutes and 20 seconds. So we'll continue to improve the robot that way. And lastly, I want to show you a task which we couldn't even do with the same hardware a year ago. Here's the robot doing machine tending. It's, and again, this is not programmed. This is just a technician showing the robot what to do. And it's figuring out how, it's putting a part in there, it's going and getting a pin, putting the pin in, and then using this pressure machine to drive it in for a force fit. So, 2 things here. One is the precision of these tasks being done by the robot by using force sensing, and the other is there is no programming here. You just show the robot what to do, and it can continue to do it. And in a second, it's just going to show one last task. In this next case, it's electrical distribution boxes where it has to punch out a piece of perforated metal. We'll see it, that again. And again, it's aligning by force, by pushing against the back there, and then feeling the force and disposing of the part. So these are the sorts of things we're getting a robot to do. One of the reasons we put it out there as a research robot is that we want thousands of people being smarter than we are, making it do things which will be helpful for elder care. Because I'm getting old and I want robots to help me soon. So please work hard and help me out. So that's what I wanted to share with you this morning. I think we're going to take questions. Is that the deal? So if there's questions, please.
Hello.
Okay, first of all, welcome to Brazil. It's really nice to see you finally, because my first international trip to the US was to your lab, but I could not schedule a visit. And then we went to Japan to meet Professor Asada, and I was not there also. I was his student and I could not meet you. And finally, you are here.
Okay, we'll hug in a little bit.
Yeah. I have a few students working on series elastic actuators for, we are trying to make it modular so that we can use these modular servo motors and make it so that people can easily attach to different robots and so on. Because usually the way it works now is that you have to design these into the different robots, and each time it's different design. So I wonder, I would like to have your point of view on why there's this debate between real elasticity with springs or software compliance with impedance control. And also, if you can talk about the research version of Baxter, I would really be glad to hear.
Okay. Well, we clearly believe that by having the real spring there, you get a bunch of benefits beyond the software impedance control. And the three things that I say we get out of the spring are: one, the physical spring with a physical spring constant actually is faster than any computation. So when there is a collision, it absorbs some energy very quickly and protects the gearbox. Then, in the next few milliseconds, you can dissipate that energy through the circuit. So there's protection of the gearbox. There's with the software, you can very easily and at a higher bandwidth vary the effective compliance in a joint. Make a virtual spring constant over a fairly wide range and change between stiffness and not stiffness and not affect your force sensing potential. So that's also important. And then just because they operate so well and so quickly, the safety. When I see some of these other arms which are using impedance control, I don't put my head in front of those arms. I don't find them to be safe. Let me just say about the Baxter Research Robot. The Baxter Research Robot is exactly the same robot as the manufacturing robot. Right now, we just have a truncated version of the software, the ROS software on the Baxter Research Robot, and open up the SDKs. Over the next 12 months, those two versions of software are going to merge, and the SDKs will be available at all levels. So all the software that we provide will be available through SDKs for the research version. So we think that's important to get to much higher level tasks with the robot more quickly. We've got an open interface at the end of the arm to try to make it easy for people to build new manipulators and experiment with manipulators on the end. And we'll be extending that capability over the next 12 months too. So.
Oh, absolutely love your talk. Thank you so much for that. So quick question, you mentioned about mobility. So of course you see a lot of soccer here, but we also have the Rescue Robot League, which is mostly tracked robots. And compared to the DARPA Robotics Challenge, which is all legged robots tackling mobility challenges. What's your opinion about, again, solving the problem using legs and walking versus using tracked robots and some of the mechanical simplifications that occur from that?
Yeah, so at iRobot, we built generation after generation of robots which you haven't seen, which were to go up and down stairs in homes, home robots to go up and down stairs, using variations on tracked systems. They all damaged the stairs, but they were not things we could sell into people's homes. If we're going to have these robots as elder care, they better not damage the stairs. They better not damage the house. I may be wrong. I'm guessing very nimble legs are most likely to be the solution, but it's early days. Hardly anyone's got anything, so maybe there's some inventions there that we weren't smart enough to think about. So maybe it turns out to be some sort of track thing. But if I had to bet money on it, I'd say much better nimble legs. And how you do that with electric drives is a challenge. So if I knew the answer, that's my point. It needs thousands of people to work on it to find the answers.
Basically the same question for the arms, and in particular for the ends. I have seen recently this, not a grasping device, but using the principle of the octopus, right? And all of your applications have these sucking mechanisms. For this, you launch this challenge for manipulation, thinking about the end, but maybe there are also alternatives.
Yeah, absolutely. Maybe it's not. Maybe, if someone can build an elephant trunk, is quite amazing. An octopus, yeah, but it requires, I think, the mechanism and the algorithms and the materials all at the same time. I'm not saying what the solution should look like. And maybe for some applications, that dexterous hand should not be on the end of the robot arm. Maybe it should be sitting here on the bench where you've got lots of ability to have lots of wires and stuff, and a dumb hand puts the thing in the you know, what was that TV series, the Addams Family. It puts it in the hand, and the hand does the dexterity, and then the robot arm is just dumb. So it could be totally different decompositions of the problem. Yeah, I'm please invent things, please. Yes.
Hi, I'm Marcos. I work here in Brazil in one professional one organization to offer professional courses for Brazilian youngs and the people here in Brazil. Congratulations for your presentation. Can you talk about the social impact the using robots at home or at work or at industry? What's your opinion about what the people perceive this in interactive co-works, how to talk in your presentation? Okay?
Yeah. So what happens in the United States is that the press gets stories and says, oh, robots, they're taking people's jobs away. Robots are taking people's jobs. And I don't actually think that. I'm not afraid of robots taking people's jobs. I'm afraid there won't be enough robots to do the jobs we need them to do. And by analogy, let me talk about computers. Back in the 1960s, when computers first came, the press story said, computers are going to take away everyone's jobs. And oh, by the way, computers are going to take over the world and get rid of us. That didn't happen, but Arthur C. Clarke, science fiction writer, is alleged to have said, you can find it everywhere on the internet, it says he said this, but I can't find where he said it. He's alleged to have said that people overestimate technology in the short term and underestimate it in the long term. So I think today when people say robots are going to take away jobs, they're overestimating it in the short term. But I think they're underestimating how pervasive robotics will become. And likewise, with computers. When computers came out in 1960s, 63, people said they're going to take away everyone's jobs. Well, they didn't take away jobs. It took a long time for them to change the workplace. So people overestimated computers. But if you look at the science fiction of the time, no one predicted that 50 years from then, everyone would have the world's knowledge in their hand. Which we have the world's knowledge. We can look up anything. We can look up, in our hand. No one predicted that capability. So we completely underestimated the power of computers. And I don't think, that we, as people, want to get rid of smartphones. We like smartphones. We like having all those information sources. And I think we will like having robotic devices helping us do all sorts of tasks. And 50 years from now, we'll say, how come they didn't realize how important robots were going to be? And I think robots are going to be as big a change in our world as information technology. We're just underestimating it right now. Oh, and by the way, who's going to do that stuff? People who played with lots of robots. Oh, I see a few of you here. Okay, change the world. Okay, the last question.
Thank you very much for the nice talk. Can you elaborate a little bit more about the design of spring using the arm control? If there is any special material to be used?
Oh,
Another question about how to handle messiness. You don't comment anything about that.
Oh, okay. So the springs, actually there's been a host of papers on series elastic designs. Probably more than 200 papers. Different ways of building the springs, different ways of sensing the spring, the displacement. So there's lots and lots of literature on that. Lots of people have worked on that. On the messiness, what I was saying was these low-cost 3D sensors let us get the data about messiness. We didn't have that before. So now lots of people can work on the problem. And the messiness problem is dealing with the clutter. You might have a pixel-based recognition algorithm that works when this object is clear and open, but when it's clumped up, those algorithms don't work. But the 3D sensing is the start of pulling apart the data so you can apply the algorithms and segment it. Okay, thank you very much.
Thank you very much. Ronaldo.
Now we will start the teaser presentations. Ask the presenters to come here. Good morning.
Ladies and gentlemen, allow me to introduce an event-driven firmware for servo motor control. From the University of Manitoba, I'm Jeff Nagy, and I have a few questions for you. Next slide, please. Does your humanoid robot fall over more often than you'd like? Are you having trouble getting sensor data such as temperature, position, and torque from your servos fast enough for your application? In general, are you having trouble controlling large numbers of servos for your application quickly enough? If you've answered yes to any of these questions, then your servo firmware may be too slow. At the University of Manitoba, we've developed Dorkius, a fully interrupt-driven operating system with a very fast communications protocol for the Robotis AX12 servo motor. It supports communication baud rates as high as 1 megabit per second, and preliminary results have indicated that we can communicate with our servos from a master controller with speeds up to 10 times faster than the original Robotis firmware for the AX12. Thank you very much.
Hi, my name is Tomoichi Takahashi. My presentation is how can the RoboCup rescue simulation contribute to the emergency preparedness in real-world disaster situation. Next one. Okay. My question is, how will rescue simulation contribute to real world? In Fukushima, real rescue robot can really contribute to the search of the disaster area. And rescue simulation started in 2000. Motivation is 1999 Hanshin Awaji earthquakes. From now, we have several earthquakes. And my answer is challenge to verification and validation program, providing evacuation plan to make available safe escape time. You see, we have, for example, 2016 RoboCup. Then this year we have the image of the building, so we can plan evacuation planning and contest how we evacuate. Thank you very much.
So good morning. Our paper presents the Northern Bytes software architecture, which is called RoboGrams. I'm Elizabeth Mametop. And the story behind this is our team wanted to upgrade to a message passing architecture, but we couldn't find anything off the shelf that we wanted to use. So, next slide. We developed RoboGrams from the ground up. This is an overview of basically what it does. But some of its best features are it's extremely lightweight and also really minimalistic. So it's actually implemented entirely in one header C++ file combination. Also, it provides data safety in a multi-threaded environment without sacrificing efficiency, because all of the messages can be accessed by reference due to our super efficient implementation of reference counting with some custom x86 assembly. Also, it's all open source, so you can check it out online.
Okay, good morning. My name is Rodrigo Ventura from Instituto Superior Técnico in Lisbon, Portugal, and the paper we are presenting targets long-term reliable navigation of mobile robots targeting domestic environments. The next slide, please. Okay, so our method, our approach is based on the motion planning based on fast moshing, and fast moshing is a method that has very interesting theoretical properties, namely creates a potential field without any local minima, and following the gradient we have the optimal goal to the optimal path to the goal, and also is a linear algorithm, so it's very efficient. And then for the guidance and obstacle avoidance, real-time obstacle avoidance used a dynamic window approach, which is an optimization-based approach. Next slide, please. And so for we have presented some experiments on the paper. We have reported so far in total more than 40 kilometers of autonomous navigation in office environments. And we are using this robot. You said a unidirectional robot developed in the context of the Monarch European project. And in the paper we report a controlled experiment to the ground truths to evaluate together with the randomly walking people to evaluate how it is cope with moving obstacles, and also a long-term 3-kilometer test in the paper. Thank you so much.
Hello everyone, my name is Jose Sanchez. I'm studying in the University of Bonn Rhein-Sieg, and we want to have our robots safely grasp persons. So this is one of our long-term goals, to help elderly in their homes, and we want to use the tactile sensors of a robot to see when we have too much pressure, and hopefully reduce this pressure and don't hurt anyone. And next slide, please. Here you can see the fingers of a robot. It's a Carabot 3 with a SDH hand 2 with 6 phalanges. Each phalange has one tactile sensor, and on the right you can see the one visualization of the tactile sensor. Thanks.
Hello everybody. So in this work we have been doing RoboCup at spoken corpus, which is a data collection of spoken sentences that have been collected during the past RoboCup by some people of RoboCup at home, and then we have been realizing this data set. I think that in addition to the specific data set we have been realizing, I think that RoboCup in general offers a very good opportunity to create data sets for benchmarking, and this should be applied also to other leagues and other tasks. So if we can go one slide more, no, one more please. Okay, so this is what we have done. We asked many of you at RoboCup at home to speak some sentences that are related to at-home robots, so domestic environment, and where we did a lot of analysis and annotation of morphology, syntax, frame semantics, and spatial semantics. This is available on a website. The next slide, please. And this website is available for download of this corpus, and there are other 2 corpus. And I think that this will help a lot of development in speech recognition, especially for Tom teams. Thank you very much.
Hello everyone, my name is Subramanian Ramamurthy. I'm really presenting on behalf of Gwendoline Schropp, who's a student from Utrecht University and who visited my lab. This work is about formalizing a new problem in the SPL. So you see in that picture above a coach robot that we use throughout the tournament. And the question she was asking is, how do you say what the coach should do? And she was bringing complementary expertise in logical formalisms. So she took all of the rules of the coach in the game and she wrote it down in a logic that both express what is permissible, what happens, and so on. And she combined it with experience in my lab, which is in probabilistic learning and trying to ground the logical symbols into what's going on pitch. And so this paper talks about how this is done at the level of specification so other people can go and implement it the way they want. Next slide, please. So here are 2 examples of the pictures. If you can't read these pictures, then it's in the poster and you can go see it. And this shows you 2 different aspects of the problem. One aspect of the problem is who speaks to whom, how does information flow, and who has authority. The other aspect of the problem is when you are making a decision or when you're doing something, then what are the things you're worrying about? How do you take the variables? What is permissible? What should you assume, and so on. Thank you.
My name is Tomoichi Takahashi. Did you enjoy last day human and robot circus? At Atlanta, I really impressed. Next place. My question is, here is a parameter of the human full soccer games, professional, junior high school, elementary schools. Please check my draft. The parameter is the same for these games. And this one is mini soccer games, futsal and glide soccer. The parameter is really different from the full soccer. And following is a RoboCup suckers. They are different from the real suckers. So I think can present real rules realize our dreams. 2050, our robot can play with human suckers. So my answer is, I think our community should set some goals. For example, futsal games or elementary school levels. And next challenge is communication between robot and soccer players, human referees is necessary. Because in playing humans, robot soccer can really complain to the judgment or a human play. I think it is necessary. So our community should set such a problem, challenge as a homework. Thank you.
Hello, my name is David Freeland, and I'm doing towards rapid multi-robot learning from demonstration at the RoboCup competition. We have a very unusual goal at RoboCup, and our goal is to take robots, which are completely blank, and then teach them during the 2-day preparation period at RoboCup how to play collaborative soccer. Next slide, please. This may sound insane, but over the last 4 years, we have made significant progress over this goal. This year, we managed to train 3 collaborative attackers to play soccer and field them into the competition. Thank you.
Twice.
Okay, twice it works. Good morning, my name is Luis Oliveira. I come from the University of Porto, and I'm presenting the work entitled RF-based relative position estimation in mobile ad hoc networks with confidence regions. And our objective is to obtain the relative positions of mobile robots using RF-based ranging estimates only. So from the estimated pairwise distances between robots and from the variances of those estimated distances, we intend to obtain the positions of the robots with some confidence. For that, we use multidimensional scaling technique to transpose from distances to positions. But because there are some ambiguities between different processes, we need to use some rigid motion transformations in order to make them compatible with each other and then filter them. Our results, our simulation results with a team of 5 moving robots in a 28 by 14 meter arena show that we have an average error of 1.3 meters and about 80% of the ground truth positions are within 3 standard deviation ellipses and 95 within 5 standard deviation ellipses. So thank you, that's all.
Good morning, everybody. I'm Leandro Tomé Martins from Universidade Federal de Santa Maria, and in cooperation with Westphalia University from Wolfenbüttel, Germany. Next slide. I'm going to present a modular and compact device to allow conventional stiff servo actuator to be easily upgraded into series elastic actuator. Next slide, please. So, adding this design to the knee joint of the humanoid robot, we can have complete joints in these humanoid robots, and it's important to have the robot walking, running, even jumping. And this is a low cost and open source and open hardware design. So if you want more details, just come to the poster.
Okay, this is the end of the first teaser sessions. These posters are now near the coffee break that will be served outside the hall. Thank you. It comes back at 11. Okay? Thank you. Hello? Hello? Okay, we'll start now the first oral presentation, first session, with the paper called RoboCup at Work, Competing for the Factory of the Future, and will be presented by Gerhard Kraftmark.
Thank you very much. So, actually, RoboCup at Work in a nutshell is quickly told. The idea was to extend RoboCup with a league which is attractive to industry and to target new challenge problems for industrial applications and basis competition by combining ideas that are already have proven to work in other RoboCup challenges. One is the fascination of competitions, RoboCup Soccer. The second one is rigid evaluation by well-defined measures. So we look at RoboCup Rescue. And the third is a stage sequence of increasingly complex tests as done in RoboCup at Home, at least so far. So the potential application scenarios we are looking at are loading and unloading of containers, pickup and delivery of parts. Again, each of these tasks, of course, comes in a large variety of variations. Objects are the same or different size, or delivery and pickup from structured or unstructured storage and heaps. Operating machines, including pressing buttons, opening, closing doors and drawers, and similar operations with underspecified or unknown kinematics. Usually we do not have these kind of things very precisely and readily available for use and manipulation. Planning and scheduling of production processes, both of them are really interesting AI fields, and it would be a possibility to integrate them more in RoboCup. Cooperative assembly, collection and transportation, so everything that has to do either with working several robots together or working robots and humans together. The targeted robot platforms are actually the KUKA U-Bot, which is a platform that is most commonly used so far. But when we conceived the competition, actually, we also thought of larger, similar kind of robots. This one is a robot that was developed in a European project with Fraunhofer, IAS, or having robots like the Baxter. What kind of objects are we using? They should look industry-like. Yeah? So that means often that they do not have color and other features that we commonly have when we talk about household objects. So most of our objects are either black or silver. In some cases this is the only distinction between them. And we have like nuts and bolts, aluminium profiles, various kinds of bushings and similar kind of things. So the research issues and challenges we have in this type of applications range actually the complete range of problems that we have in robotics. So they are very difficult perception problems. Even navigation is not very simple because there is no such concept as a well-defined target position that you can attain, and the robot must infer itself what a suitable target position would be when moving through the environment in order to have a good grasp of an object or to perform a particular kind of fitting, for example. Grasping is a widely open problem. There are a huge variety of much more complex shaped objects than the ones that I have shown. So this is a very interesting field which can be readily studied in this context. And of course it has a lot of relationship also with RoboCup at Home, where we also have the problem that we phase. For example, imagine a set of plates stapled on top of each other, and the task is to take just one of them. Human-robot interaction and cooperation. Again, these touch everything that has to do with robot interacting with humans in a more natural way. Industry is actually used to tell robots and task in terms of positions. Everything is given as positions in coordinate systems. When a human is supposed to tell the robot what the task is on a more abstract level, we need to look at a different level. Okay, some general ideas about the competition design. Three main items here: public appeal, competition structure, and scoring and ranking. As for public appeal, we should look at tasks that are easy to understand. So what is the robot supposed to do should be easily recognizable when looking at the competition. It should also be easy to observe if the robot is well doing. Yeah? So is the robot actually doing what it's supposed to do? The competitional structure, as I already said, we try to get inspired from RoboCup at home. So a sequence of tests, but we also include more repetition of tests to test for more robustness and to test more variability. So the same kind of tests would be repeated, maybe with some variation of the objects involved, the environment set up, or different kind of settings. And finally, scoring and ranking. So we try to define really clear objectives and performance criteria. So robots do not get points for very simple kind of things. They actually have to find the objects and grasp them or put them into the target positions in order to score. The overall ranking is then determined as an accumulation of the scores, where some weighting might be in place for accounting for the different kinds of difficulties. We do not have this yet, but this is clearly on the agenda eventually, that we also have best-in-class awards like Rescue and other leagues are doing this successfully. So when we started, we actually thought about what kind of tests could we do. And we thought, let's start with something very simple, where everyone claims this should actually work out of the box. And we kind of expected or hoped that every team would be able to do this in the first year already without any difficulty, right? Because if you download ROS, supposedly navigation comes out of the box and so on. So we conceived a basic navigation test, where the task is to demonstrate the ability to safely navigate. However, the navigation task is given as a sequence of symbolically specified poses. So for example, this red string here is such a specification, which consists of a sequence of triples with a symbolic description of a place and the environment, an orientation, and a timing where the robot is supposed to stop for a particular amount of seconds in order to indicate that he reached the position. The basic manipulation test is similar, actually demonstrates the ability to manipulate objects, so pick up the objects, put them onto the robot, and or take objects from the robot and place them in particular configurations. And the third test would actually combine these two so that we have a basic pick and place task of transporting objects from A to B. So the kind of environment we designed initially was actually meant to simplify things really. So the purple lines, of course, were not in the environment. We only had markers for these symbolic positions. We had various kinds of source sites and destination sites where objects could be found or deposited. We have certain walls, and the little geometric kind of tags that you see here were meant to disambiguate the environment to really make the navigation simple and not make it difficult. It turned out that nobody used these kind of things, and we did away with it very quickly. So in a second repetition of the test, then for example the environment could be changed and we could place objects or obstacles in certain positions in order to make the navigation more difficult. And the combination would then look something like this. So if you have a sequence of 4 or 5 of these symbolic places, then it's a fairly reasonable navigation task in a factory-like environment. How does it look in practice? So meanwhile, our environment in my own lab looks, for example, like this. So you don't see any of these tags. The environment is not completely walled off, it is open. And if we look at the environment, for example, used at the German Open, there were some generic tags used here, but there was even more open space, so only some or few walls are actually present. So it actually turned out that these basic tests were much more complex for the teams to solve really reliably. Partially that was due to the robot still being not as robust as we hoped, partially to the software that was used. But right now we see in the current competition actually that was actually much better. And the challenge actually is to do really industrially relevant stuff. So 2 further tests are the precision placement test, so where the robot should demonstrate the ability to place objects very precisely, and a conveyor belt test which would introduce some aspect of dynamics and involve moving objects. So to give you an example of the precision placement test, let's assume the 2 aluminum profiles we have here. We designed various kinds of cavities that you see at the lower part, where in each of these cavities, each of these profiles would fit. And the difficulty is, of course, different. Here, the object would fit in the horizontal manner completely through. Here, you have to, it requires more precision. It would fall through only if vertically inserted into this cavity. And here it is even more complex because there are notches here that would precisely have to fit into the respective cavities of the aluminum profiles. Yeah? And we have actually, each of these cavities are 3D printed plastic parts, and we have designed different ones for each of the objects we have in the competition. The actual setting in the environment then looks like this. So we have a dock where 5 different such cavities can be placed. You could also place fewer ones. There are such plates which just cover the holes. And this allows the specification of fairly complex tasks, like in fetch this particular kind of nut and insert it into the respective hole here, and get a bushing, insert it here, and so on. The second one actually is this picking objects from the conveyor belt. So the idea is that there is an area here, the rectangle that you see. Oh mine, it's almost empty. So the robot has to go into this area, and when the robot is in this area, then the belt would actually start, and objects placed on the other end would actually move to the other end of the belt where the robot has to take them. The actual implementation of the belt in our lab is seen on the bottom right. Okay, so these are the tests so far that have been actually used in competitions. Of course, we have many more ideas how to take this a step further. One competition where we actually do this is within the European project ROCKIN, where we have the ROCKIN at Work challenge, and together with KUKA's labs, actually we designed further tests which involve assembly of parts and similar kind of activities. Sorry. So once you have a design for a new competition, the question is how do you get it off the ground? So we actually started with organizing a camp in our lab in May 2012, where we had about 15 to 20 people coming from different universities, one team from Turkey, most of the others at that time were from Germany. Then we actually held the first competition also at RoboCup 2012 in Mexico, the first demonstration, and another one at IROS 2012 in fall in Portugal. And this is a photo of the RoboCup German Open this year with, I think, 4 or 5 teams have been participating there. Most of which, or all of which, have been participating here as well. I'd like to finish the presentation with a small video which shows a few sequences. This starts with the conveyor belt test, so the robot grabbed the aluminum profile. This is actually the robot of the WF Wolves, team from central Germany, so to speak, northern part of Germany. Then we see here the robot picking up various of these objects at IROS 2012. We also used various boxes, and one of the tasks in this competition was to pull the boxes out of underneath the docks, and we used some of these markers also for identifying these boxes. And here's an example of the precision placement test, so the aluminum profile has been done. I think these are the Lubots, correct? So now they use a Kinect camera actually on their arm. Now they scan the whole environment. Of course, in principle, this needs to be only done. It's done in a few seconds. And now it finds the right cavity. It has to turn the arm in order to not, that the camera is not in the way, and then places. Okay. Thank you very much.
Any questions?
I'm wondering if you're considering in the future to introduce also multi-robot collaboration as another challenge.
Excuse me. Yes, of course, it was in the plan from the very beginning. That it was not happening so far had to do with that initially there were some problems with the robustness of the arm, and the teams were too much afraid if several robots would operate simultaneously in the environment and the arms stretch out that they would get damaged. And yes, it's a problem to be solved, but we have to push the teams to actually tackle it.
We have time for one more question.
So, are there any possibility to introduce messy factor? So, in the talk of Professor Brooks, so he mentioned the 3 key concepts: mobile, manipulation, and messy. And now, your field is very clean, maybe so for robot, and but in real world, so it is more messy thing. So it makes more application oriented or something. So are there any possibilities of?
Yes, this is definitely the case, but as I said, many of the things when we started turned out to be much harder for the teams than initially anticipated. And there are actually two kind of things. So you could have, for example, a pile of such aluminum profiles, or you could have 20, 30, 40 of these nuts in a box, and the robots have to cross several of them. It's actually an open question. To me, I think it might even be easier to grab an object if they are messy in the box than if they are nicely sorted. I think it is very difficult for such robots, if you have like aluminum profiles in a box, neatly arranged, then to grasp them might even be more difficult than if you just throw them in. There's another question there.
We have to move on, okay? I would like to thank Professor. I'd like to call the next speaker. Yes. Mikhail Prokopenko, that will present the paper Simulation League's Analysis of Competition Formats.
Thank you. So the presentation is going to be fairly simple. We'll look at the Simulation League. I will not really be introducing Simulation League as such, and the talk is not really about the intricacies of simulation, but what you need to know is that it's fairly easy to set up, much easier than robotic leagues. Each game takes about 10 minutes, and it's possible to distribute it across, say, cluster computer, supercomputer, and you could play 1,000 games literally each hour. So that's the fact that we will be exploiting quite well. So analysis of competition formats is the real topic of this presentation, but I will touch on some other subjects. It's a result of collaboration with David Budden, University of Melbourne. He was a vacation student at CSIRO, and the rest of us are from CSIRO in Sydney. So, Simulation League has been a part of RoboCup since the very inception, and I believe truly it's a critical part of RoboCup. So, what it gives us is a real tool to investigate system-level perturbations, because you could really consider multiple scenarios, you could play with different variations, tactical behavior. So it's really powerful mechanism to investigate how changes in, say, individual skills affect team play. So one of the research goals for the whole development here was to investigate how this system-level effects can be traced. But specifically, and I will focus mostly on that second part, is the question, what competition format is best for the Simulation League? It's arguable that the results that we present could be even transferred to other team sports, but at this stage, let's limit the scope to the Simulation League. So I will introduce a simple enough methodology which allows to compare different competition formats, and we will focus on top 8 teams using results of 2012 RoboCup in Mexico, 2013 RoboCup in Eindhoven, and comparing different formats. So let's move on and just look at Simulation League in the context of the RoboCup overall, right? I mean, we have so many leagues, and some of them fairly old, some of them fairly new, and it represents in general quite a diverse range of cultures, countries, approaches to science, and so on and so forth, right? So what I would be arguing about is that Simulation League is one of these leagues which in fact provides financial inclusivity for the RoboCup initiative, and we have some fairly simple analysis of that, but I will show in the next slide. And I did talk already about investigation of statistically significant effects of system-level perturbation. So let's have a look at these two plots. So what we've done, we compared across different leagues, and that's on a horizontal scale here, the average financial characteristics like GDP of countries which represent, which participate in each of these leagues. And on the right-hand side of the horizontal scale, you have 2D simulation, 3D simulation, and rescue simulation. And on the left-hand side of each plot, you have the hardware robotic leagues. You could see that just by this simple analysis, the GDP of countries which participate in simulation league or simulation leagues is actually much smaller. So which kind of shows you that just to maintain financial or economic inclusivity of RoboCup, simulation leagues are quite powerful mechanism to ensure that. But enough of that. Let's move on to the main topic, and I will not argue anymore that the simulation league is something that has to be a part of RoboCup. I will really move to the way we investigate multiple competition formats. So again, focusing on top 8, right? So you have top 8 teams which you selected from some preliminary round robins or whatever, and now you need to find the best way to identify true ranking, or as close to true ranking between these 8 teams. Obviously, the dumbest way is to just do random assignment of places and go home. So that would be the extreme. The other extreme would be to play, say, thousands and thousands and thousands of games between every 2 teams in this top 8, and then arguably that would provide some true ranking in a round-robin format. That would achieve the goal, but it's not really possible in a competition in a day. Usually you want to achieve it in a day. So somewhere in between lies the compromise between the true ranking and the practical implementation of it. So what we've done, we did play these thousands and thousands and thousands of games as an iterated round robin to identify true ranking. Obviously, we've done it much later after tournaments in 2012 and 2013, and that basically gives us ground truth. Then we compared with this ground truth a number of possible formats. And by no means I claim that this is an exhaustive list of possible formats, but those are the ones which people are familiar with. Like say at the World Cup, we use single elimination, knockout. In some leagues, people do use round robin. You could look at the double elimination, and traditionally in simulation 2D, double elimination format is very popular. It has been the one in use for, I think, 15 years at least. In 2012 in Mexico, we tried a hybrid. We split top 8 in 2 groups of 4. They played round robins in each, and then top 2 teams from each advanced to semifinals and the final. So you could analyze these formats in terms of number of games they demand, and also in terms of how they approximate that true ranking by comparing these rankings as vectors of integers. And I'll show you that in more detail on the next slide. So let's actually talk a little bit more about how we did this 1,000 games iterated round robin. Like I said, we played 1,000 games in each pair, and there are 28 games to play in a group of 8, so that's 28,000 games. And that immediately presents you a dilemma. How do you actually average the results? I mean, in normal games, when you have only single game between 2 opponents, you get 3 points for a win, 1 point for a draw, and 0 points for a loss. But if you play 1,000 games, these averages, you could get something like, let's look at maybe Team Right Eagle versus Team Gliders, our team, and Right Eagle gets 2.397 on average points out of 1,000 games. It would, in reality, if you play just one game, get approximated in a discrete way to 3 points or maybe 2 points. But you can't get 2 points in the game, right? It's either 3 or 1. So the dilemma is you either use continuous points like that, or you translate this continuous point into 3, 1, or 0 in whatever way, or maybe even 3, 2 if you want to take this compromise and then determine the ranking. So we will be really using, we kind of have 2 ground truths, one continuous and one discrete. So now let me actually introduce the metric that we use for the comparison. So on the very left, in the left column, you have the actual rankings of the teams as it happened in 2013, right? And they're actually ordered in that ranking. That's the leftmost column. The rightmost column is actually the ranking produced by this iterated round robin. And you could see that the first 2 follow it, but for example, team number 3 should have been number 4, and team number 4 should have been number 8. So this difference between rankings, if you compare left column and the right column, gives you, using simple L1 norm, discrepancy. And in this case, it is actually quite large, 12. So basically you see that some teams were arguably unfairly lucky, and some teams were arguably unfairly unlucky. So again, so this gives you kind of a comparison between 2 formats. One which was used as double elimination and the true ranking. In a continuous sense, had we been digitizing or discretizing these scores, we would be getting either 3 points or 1 point or 0 point, and that is shown on the next slide. In this case, what we did, we look at average scores, not in terms of points, but in terms of the goals scored. Say we look again at right eagle versus gliders, and the average score was 2.5 goals in the game versus 0.7 goals in the game. That would result in a, obviously 3 points to right eagle and 0 point to gliders. Then you sum up all these points and you get slightly different, possibly slightly different rankings. In this case, the only difference between this one, discrete and continuous, is teams 3 and 4 flipped up. But again, the difference between actual ranking achieved in Eindhoven and this discrete is 10 virtual points, which is arguably quite large. Okay. So what we do now is we propose a format which we believe is most faithful in this situation, top 8 team, and we analyze that format in terms of proximity to the true ranking. This format that we propose is not rocket science. It's again a single round robin, and then classification games between first and second, third and fourth, fifth and sixth, 7 and 8. How do you get this single round? You could obviously sample, and we did sampling from this iterated, we sampled 10,000. But what you see here in the table is actually a combination of real results from Eindhoven, if these 2 teams met in a double elimination, plus some gaps were filled by average scores from the iterated round robin. So this one gives you ranking on the very right-hand side, and this one differs from the continuous ground truth by only 6 virtual points. And if you compare with the discrete, it differs only by 4. So arguably it's a much better, much more faithful representation of a true ranking. Okay, so is that believable enough? It is, but and that's the point of having simulation league. You could actually investigate statistical significance of all of that, rather than showing you one example. You could actually sample thousands and thousands, 10,000s of round robins, or single elimination, or hybrid single elimination, or double elimination, and compare with true rankings in terms of the proximity. And this is what you see here. On the left plot, you have 2012, which I didn't talk about. On the right-hand side, 2013 top 8. Let me explain what these curves actually represent. On the horizontal, you have the actual distance between ground truth ranking and a particular sample of, say, a round robin or double elimination or single elimination. On the vertical, it's like a histogram, pretty much. On the vertical, you have some probability, or basically probability, of how many times this particular L1 distance was achieved, or probability of that particular L distance to occur in this iterated round robin. So what you want from your format is that it is quite heavy, quite high in the low L1 distances, and it is quite low in probability on the right-hand side. So, for example, the red curve here, which represents the proposed format, achieves that. It is better than others for small distances, and it is lower than others on the larger distances. And that pretty much completes the technical content. So I would just like to conclude with the main messages here. So we argued very briefly that the simulation league, or leagues in principle, do provide some financial inclusivity for the RoboCup initiative. We proposed and evaluated a new tournament format, and basically this could be considered as a way to investigate different formats for other team sports. Thank you.
So, any questions? Well, I have one question. In simulation, why didn't you use more statistical, use the basic statistical significances, and you have more tests like ANOVA and all that everything you could have with this?
Well, I understand, yeah. We could use multiple tests and have a look at how statistically significant is the actual result, yeah. We just thought that this direct comparison of L1 distances, probability, density, would achieve the same. I mean, we thought, in fact, by doing exactly what you said, but it would have been just showing that our format is statistically significant and nothing else. It would not directly compare with the other, even in terms of the probability distributions like this, like that.
Any questions? Okay, so I would like to thank the speaker. And now we're going to start the advancement of the RoboCup League, the advancement of the RoboCup League section. Thank you.
Welcome to the League Advancement Session. I'm Peter Stone from the University of Texas at Austin. I'll be moderating the session. And we're going to break this into two segments. First the soccer leagues, and then the applications leagues. And so the format of the session is that first in the soccer leagues, each league will have 5 minutes to present their future plans for the advancement of their league. And they've been instructed to not focus on the past and the history and how they got here, but instead to focus on the current research challenge in their leagues and what they see as the future research challenges in their leagues. Each will have 5 minutes, and then we'll bring everybody back on stage, and we'll have a 25-minute panel discussion where it'll be your opportunity to ask questions and interact with them, and then we'll move on to the applications league. So starting right away with the simulation league is Klaus Dorer. And take it away.
So hello everybody, and the paper we wrote was written together with Hidesha Akiyama and Nuno Lau. Next slide. The current situation in soccer simulation leagues is that we have two sub-leagues. It's the 2D simulation league, started in 1979, playing a simplified robot model, but 11 versus 11 games, and have the full set of FIFA rules applied, including offside. And we have a 3D simulation sub-league, which has started in 2004, and is nowadays using a more realistic robot model, the Now, which is simulated since 2007, and since 2012 we played 11 versus 11 games in that league. Next slide. What's new this year in 2D simulation is, as we heard right now speaking from Mikhail, is a new tournament format that has been used as a result of his research, what is a fair tournament model. And in 3D simulation we have a couple of new things like heterogeneous types. Let me briefly explain what this means. We have different variations of the Now robot, with some with longer legs, some with wider hips, even one with a toe. And what's very special about it is that the teams only know about these specificities some very few weeks before the competition. So it's no longer a competition in which we program for one specific robot and have weeks and months to program that, but we have to get to a point where we have algorithms that can be easily translated to other robot models. And that's what has happened, and the teams have even been forced to use these robot models. And I was quite surprised that all the teams have been been able to walk with different leg lengths, different hip widths, and work quite well. The second thing, what we did this year for the first time, was a running robot challenge. We let the robots run on the field as fast as they can, and of course we measured the speed, but also what we measured was the amount of time that they have both legs off the ground. And the sum of these scores determined the winner. And what was new in this challenge was also that for the first time we allowed the teams to specify variations of the robot model. So they could really model the morphology of the robots in certain boundaries, of course, for the first time. Next slide, please. What's going on? What will be the future of these leagues? In 2D simulation, we have a good trend in having data mining and running things on clusters. That's what's special in Simulation League, that you can run many games, as, for example, Mikhail did. But not only for analyzing things, but also for learning and learning technologies. And also what we saw is also first work reported in collaboration with real soccer games, where there was an analysis and comparison of simulated soccer and real soccer. In 3D there is a discussion that on the one hand we would want to have some more nicer games in respect to less players falling over, putting penalties on falling over, and for example enforced passes. But also what we think about is that now we are playing 11 versus 11, we also want to move closer to real robots. And there is currently evaluation going on, and you can see a poster outside. If Gazebo, for example, would be an alternative simulator which allows us to model more realistically the robots. And also, one strength of Simulation League, which is not very much exploited, but we have started, is that we are able to model the morphology, change easily the morphology of robots, and to come up with new robot models that may in the future be real robot models. Next slide. I want to show you how this games look like in the last minute. And first a scene from 2D simulation, which where you can see that it's very dynamic what's going on. This is the final of last year, and this is probably the league which looks most like real soccer when you look at the gameplay. Next one. And in 3D simulation we see a scene from the Portugal Open. Next slide. Where we see for the first time that players are passing to each other. So there was a first pass to a player, and this one is passing over to the next one, which is taking the ball. It's dribbling and passing over to a third player. So even without enforcing passing, it has started that teams that want to be strong and want to be first in the games have to kick and have to pass. So, thank you.
Okay, thank you, Klaus. Just before I invite the next person up, I just want to say, is in the audience, what we're hoping for this session is the result of last year, a challenge that the Federation made to all the leagues to think radically and to make changes and to think about how we can move forwards in these leagues towards new ideas, new research challenges, and towards sort of the ultimate long-term goals of RoboCup. So what I'm hoping you're doing as you listen here is to take it as an opportunity to get your mind out of the leagues that you typically participate in and put in sort of the broader RoboCup perspective, learn about what's going on in some of the other leagues, and also think about what you think, when we come to the panel session, what you think can be possible changes, possible research directions, possible ideas that connect between the leagues. So as I move on, the next is the small size league, and Joydeep Mishwas will be presenting.
Thank you. So the single size field is the field in which the small size league has been participating in for a number of years now. You might be familiar with it. It's about 4 meters wide and 6 meters long, and this is where we were as of last year. And this year, this is what we use for the small size league for in terms of vision. It's the shared vision system. It has 2 overhead cameras, and we can figure out where each of the robot is based on their patterns and where they are heading. And we can also find out where the ball is by looking for orange blobs in the field. Now, we made some upgrades to SLL vision, where essentially, okay, so these are the patterns which I was talking about, but if you go on to the next slide, you can see we made some upgrades to SLL vision, which actually allowed us to get away from these overhead cameras. So now instead of having overhead cameras, we can actually have cameras mounted potentially on the corners of the field, and we have a generalized setup which actually allows us to be able to have arbitrary number of cameras and arbitrary orientations around the field. And this advancement actually helped us to move very quickly onto the double size field, which was adopted this year. It wasn't compulsory. And if we go to the next slide, this is actually the dimension of the double size field. It's about 8 meters wide, 8 meters long and 6 meters wide. We still used overhead cameras this year for continuity with the previous years, but we have in mind that in the years moving forward, as we keep increasing the field sizes, we might want to move away from overhead cameras and corner mounted cameras. So some of the other interesting advancements that we have for the league are looking into automated referees. So if you look at the gameplay in the small size league, it is a lot of there's a lot of overhead to the referees in being able to manipulate the ball, tracking what's going on in the game, and taking fast and accurate decisions. To reduce the amount of cognitive overhead for this on the referees, what we would like to have is the shared vision system, provide the raw data to actually have an automated referee decide what's going on. And that's why we had this automated referee technical challenge, where essentially an off-board system would actually compute which team was at foul for essentially losing the ball off the field, or they had multiple defenders violations and robot collisions and illegal kick speeds. So this is just a small subset of the rules that we actually have, but this was what we felt was a starting point to see if we could move forward. And in the coming years, we would actually like to be able to see a robot referee actually manipulating the ball to the correct places and setting up the game for refereeing these games. Now, we have in mind a couple of future technical challenges, and these future technical challenges are actually directed by what we find is most challenging to the teams as of today in the small size league playing soccer. One of which is that we're not able to intercept chip kicks very well. What we find is that the moment one robot does a chip kick, the other robots are confused and their own team members are confused. So we'd actually like to be able to see interesting gameplay where chip kicks are actually intercepted well. Now we'd also see what we see is that when one team goes up against another, it is very, very dependent on how well the other team does in seeing how the first team scores. Now, this is not necessarily true in human soccer, for example. A good team you would expect to do well against a variety of other teams. Now, what we'd like to see is that if we have a team which has some very physical, it has some limitations. For example, it does not guard the left side of the goal. Can the opponents actually exploit this fact and be able to score more goals? Can it actually detect these kind of things? We'd like to see if we can actually have teams develop AI to actually exploit these openings. Now we also have in mind a couple of ways in which we can adopt perception for the small size league to be able to proceed beyond the double size field into the future, looking way ahead, right? And we have in mind such alternatives such as a Vicon system or even using RFIDs on the carpets, right? Now here's a proposed timeline which is keeping in mind very much a work in progress. It's evolving as we speak, as we discuss. But going right to the very end that we have, the horizon that we have right now is 2020, and we'd have automated coaching during the game, and even before that, we'd be able to increase the field size beyond the double size league. It will probably be called the quad size, where we'd have 11 by 11 robots from multiple teams, right? And we'd actually have the shared vision system used for that. So that concludes my short presentation. So if you have any questions, I'm sure we'd be willing to take it during the panel.
Okay, thank you, Jody. Next is Robin Sotens representing the middle-sized league.
Okay, so on behalf of the MSL Executive Committee, I will present the current status and future outlook of RoboCup MSL. I have a couple of pictures and some slides with text and a short video to show you. So let's start with a couple of pictures. As most of you know, we play 5-on-5 in RoboCup MSL. Teams are free to design both software, of course, but also the robot itself. While taking into account constraints on size and weight, of course. Robots cooperate through a Wi-Fi network with each other, but all sensing equipment has to be on board, so there's no central camera or there are no external beacons. Furthermore, we're playing with an official FIFA ball on a large size field, as you can see on this picture. Now in terms of rule changes for this year, we've for the first time introduced coaching possibilities, but not as a way of remote controlling. Instead, coaching can only be used for passing high-level strategic commands to the robots, and only during stoppage time, so between when robots are repositioning for a free kick, for instance. Furthermore, we've stimulated passing. We've continued doing that because we're doing that for a couple of years already in MSL. We do so by limiting the length of a dribble movement, and also by having a rule that says you have to make a mandatory pass before you can score a valid goal in case you have acquired the ball on your own hand. Let's move on to the next. Why is this scientifically interesting? We're doing multi-robot cooperation, of course. There's a lot of, it's a huge challenge to figure out what knowledge you should share between robots and how you should share information in order to make a pass. Furthermore, since robots are typically fast and a bouncing ball does not wait for a computer who has to finish its computation, real-time, time-efficient computation is rewarded. Since we're using a real ball on a field of realistic dimensions, it comes with a number of disturbances, of course, which makes it a good real-world benchmark. Teams are doing both mechatronics design up to AI. There's a lot of science in how to integrate all of that in a single working robotic system and seeing where the bottlenecks are then. In terms of perception, we're trying to balance the challenge there. So we have some simplifications to allow teams to well, not get stuck at perception and not be able to do any research beyond in multi-robot cooperation, for instance. So one simplification is that robots always have to be black, so that they can just be recognized by their color. And since we're playing 2 halves of 15 minutes, energy efficiency is also a challenge, of course. Yes, next slide. But apart from being scientifically interesting, it's also fun for the audience, as you can see by the people who are cheering in the back. Actually, the rule that stimulates passing contributed a lot to this. The passes make it a lot more appealing for the audience to see and to show that we can not only do that against a team of robots. I've put a video on the next slide. Some of the trustees will remember this, because it's a shot from the human versus robot match of this year, actually. Apparently the video didn't work in PowerPoint, but here it is. Cool. Nice. So, next slide, please. Okay, so since MSL is a relatively old league, it has been there since the beginning of RoboCup. It could be hard for new teams to catch up. Most of the teams who are in the league now have been there for 5 years or more already. So, since of course we would like to have new teams coming into the league, we should facilitate that. And on this slide I've put 2 examples of how we're facilitating that. In the bottom left you have the Robotic Open Platform, which is a website where teams can release their robot under an open hardware license. So you release the mechanical drawings, the electrical schemes and part lists. And actually a number of teams have put their robots there already. On the top right you see Turtle 5K, which is a redesign of an existing MSL robot, but focused on cost. So the redesign is done by a group of companies who are good at looking at cost, of course. And this robot can actually be built for approximately 6,000 to 7,000 euros, depending on the size of the badge. So concluding, since my time is almost up, I see. In terms of rule changes for next year, we will of course continue to stimulate passing. But also this year we've done a technical challenge on artificial grass. This is a picture of this year also, where teams had to grasp the ball, dribble, pass and score a goal on an artificial grass dirt instead of the carpet that is normally used. And well, most of the teams were able to do that actually already. So there's a good chance that maybe next year already, or the year after, we switch to artificial grass instead of carpet, which comes with more disturbances, of course. So that concludes my presentation.
Next, invite Tim Lauer to represent the Standard Platform League.
Thank you. Okay, hi. Now I want to shortly describe what's currently going on in Standard Platform League and what we think will happen for next year. Yeah, what's new this year? Please, next slide. So we introduced a drop-in competition, a new sub-competition in which mixed teams play together. Each team has, as in normal games, 5 robots, but every one of those 5 is from a different team and thus runs different software. 23 teams participated in this competition and we had an overall of 15 matches. So this means that if you participate with your robot, you have over the tournament up to 20 different teammates. So yeah, it was the first year. Last year we had this as a challenge and this is the first year we had this as a competition. And after RoboCup was over, we made the all-star match in which a mixed team played against the current world champion, and the mixed team did better than any other team in the competition before against the world champion, so they lost only 2-4. Okay, next slide. Yeah, we have a standard communication protocol this year. This is the basis for the drop-in, but teams also have to use it for the normal competition. And this should reduce wireless problems and gives the league control over how much are the robots allowed to communicate. Now we could say, okay, maybe next year a few packets less, or the data gets smaller and smaller by year to have less dependency on wireless in the future. Next slide, please. We also, similarly to the MSL, introduced coach robots. So each team is allowed to put a now on the side who can give strategic advice, which is transmitted delayed in time and only can send every few seconds one very short text message. But only few teams had this year, because you have to do a lot from scratch to have a fully working coach robot, but all teams like it, and we're very likely to see many of them in next year. Next slide, please. As a technical challenges, we had sound recognition, recognize predefined sound patterns, as well as a whistle. 10 teams participated, and almost all of them always got the whistle right. So the whistle recognition seems to work on the now. There was the any place challenge. We took a robot, a goal, and a ball to any place, which we did not tell the teams in advance. Put the goal up and the ball, and out of the box, without any configuration, the robot should score goals. We did this behind this, actually, as you can see, and yeah, goals have been scored, and some teams, but many not, made it to the ball at this place. Okay, next. No, wait, we have always the open challenge, where teams can do whatever they want, as long as it's related to Standard Platform League. So on there we had a demonstration of playing in now outside in sunlight on artificial grass. And we also had refereeing now robots, just a few examples. Okay, for next year, 2005, we will go towards white goals, as we want to get rid of this many colors, and like, yeah, this must be this yellow, so I think it's time that we go white goals and have less artificial field. Next one. And also this color thing, so in the midterm we want to have custom jerseys, so every team can make its own jerseys, like in real football, and not this predefined magenta and cyan, so do what you want. So the compromise for next year will be teams will be allowed to have, or we think, do this, to have their goalies in their own jerseys as an intermediate step towards this. Next, please. We're think about introducing a first set piece, like a corner kick, to have one more situation in which teams are forced to do passing or to coordinate in a planned manner. Next one. And we think we want to start the extra games with the whistle. So currently it's due to this wireless dependency, like wireless does not work properly. Do all robots get the packet that the game actually begins? We think about just start taking a normal whistle. Next one. And we want to continue. As I said, the coach did not run that well this year. And drop-in competition was working good, but there's much more performance we can get from the teams, so we want to advance more in this direction. I think that's it. Yeah, thank you.
Okay, and finally introduce Jackie Baltz to talk about the humanoid leagues.
Thank you. So I just want to give one slide about the past of the Humanoid League, because it explains some of the culture and the history that we have. So we're one of the youngest soccer leagues to started in 2002, when 6 teams with mostly custom-built robots, ragtag collection of robots showed up. And we competed in, at that time nobody was able to play soccer. In fact, most of the robots could barely walk, so we did penalty kicks and a free demonstration. Then 2 or 3 years later, we moved into soccer. And during that time, though, there were a lot of discussions amongst the team leaders and the participants about some of the choices that we had to make as a league. And over the years, during that time, there were a couple of things that became apparent. One of them was that the free demonstration, teams didn't really like that. They preferred a quantitative evaluation rather than a subjective judging. So we got rid of the free demonstration. If you lose a soccer match 2-0, at least you know why you lost. If you lost a judging competition, then any sort of thing could have influenced that. And the other thing is that teams felt very strongly that if we are working on humanoid robots, it should be humanoid robots that match a human. So human-like kinematics as much as the current technology would allow, as well as human-like sensing. So Omnivision sensors, we had a very successful team that used the Omnivision camera system. They were disallowed. They then had to use to a single view camera or a stereo view camera. The present, so for 2014, we took up the challenge set by the trustees last year, and we made some significant changes. One thing was that the team leaders felt we really need to push the height of the robots in order to push to the new technology that will be necessary for 2050. Electric motors, their power to weight ratio is good enough to make a good performing small humanoid robot. But if you're moving past 50 centimeters, 60 centimeters, then the problem becomes a lot harder, and the power to weight ratio of these electromotors severely limits what you can do. So in the future, we think that will lead to more interesting mechanical designs and more interesting actuator designs. And by 2050, we assume that there'll be some sort of artificial muscle that we will be using rather than a robotic servo motor. So in the Humanoid League competition, we now have 3 size classes, 45 to 90 for the kid size. They increased the most, then 80 to 130 for the teen size, and 120 to 180 for the adult-sized robots. And the adult size, they also have a 10 kilogram minimum weight in order to make that clear what the distinction is to the teen-sized robots. The size of the field was increased, and the number of players were increased. Now, today, the walking on even flat surfaces is not an issue for most teams. Walking on this kind of surface, a carpet, has been solved. So what's the determining factor, what determines the performance of a team most at the moment seems to be localization and mapping. And what I mean by that is localization, where is your robot on the playing field? And mapping, of course, you know where the goals are, but where's the ball and where are the other players on the playing field? For the future, we have been following a TikTok model as far as the rule evolution is concerned. So we have major changes every 3 to 5 years and intermediate changes that allow teams to catch up to the new rule development in the intermediate years. And we're trying to push on 4 fronts. We're pushing towards more human-like players, which means we increase the height of the players. We overlap the sizes of the players in order to allow teams to have a gradual evolution from the kid size into the teen size. So you can build a large kid size robot that will still be legal to perform as a short teen size robot. More human-like soccer fields, so we removed colors. More human-like matches, longer duration of the matches, power efficiency is important. And more human-like rules, actual corner kicks, throw-ins, and free kicks. Yeah, okay. So the research directions, walking, active balancing, AstroTurf Challenge this year, playing full games outdoors. By maybe 2020, teams felt running, jumping and heading, ball handling, human-robot, robot-robot interaction, and more team play. So we want to introduce rules that force us to force teams to make passes. And that's the end of my presentation now. Thank you.
Okay, so now I'd like to sit here. I'd ask, join me in Jackie with Tim, Robin.